Now let's do another example about these electric field lines. Let's suppose that we have plus 2q charge over here and minus q charge over there. What will the electric field lines look like? Let me give you some choices. You will. Okay, so this is one. No. So what do you think the electric field lines will look like? A. So so you are saying that it will look more or less like the previous case, right? Okay, they will be closer, but more or less the same. So let's say this is the second choice. This is the third choice. And the fourth choice. Okay, how many A's? Okay, how many of you think that the field lines will look like A? Let me add a few more lines there, if you don't mind. A's. Come on, I want to see some hands. Just only you? Okay, B's. B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. C. D. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that makes a total of 10, 22 answers. Okay, so it's not A, it's not C. It is either B or D. So among the B group, why B? No, let's start with the D group, why D? You think the answer is D? Okay. Okay, so that's an answer. Any of the B guys? B? You are still, no, I want the B guys. So here there's an explanation. Your friend is saying that the electric field created by this positive 2q will be larger. So it will be more dominant unless we are very close to the charge minus q. So it will look more like the electric field of the plus q charge, less like the electric field line of the minus q charge. Now, the B guys, do you agree with it? If you don't agree, what's your reasoning that is B? Yes. The directions. So you still think it's B? Okay. Okay, the number of electric field lines, do not pay too much attention to the number of electric field lines. It's just a personal choice. How many electric field lines would you like to show? I mean, you can increase the number of electric field lines, reduce the number of field lines. Now, let me see, 1, 2, 3, 4. There are 5 lines here. Here also there are 5 lines. So number B and number D, they have the same number of electric field lines. Hmm? No, they're both positive Qs. Well, of course, I mean, if you draw like 10 lines passing through the positive charge, you should draw only 5 lines passing through the charge minus Q, entering the minus Q. Oh, here now I have 10 lines from here, 5 lines over here. Now I should have the same thing over here. Let's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here I have the 5. So the answer didn't change. So you still think it is B? Why do you think it's B? I mean, you like it more? Okay, so your friend is saying that the more charges attracts electric field lines more. What does it mean? Electric field lines doesn't have any charge. So they do not, I mean, if you want to make this force analogy, electric field lines will not feel any force. So there's no point in saying that they will be closer to each other. Okay, who else who still think it's B? No, okay, so let's keep step by step. So you are saying that plus 2Q charge will exert more force on what? Hmm? More than which one? Okay, so if I put a test charge over here, the plus Q charge will exert a larger force in magnitude than the minus Q charge, okay? Now hold on, he's still continuing. Well, you see, if you put some test charge, its trajectory will depend on the forces. So the trajectory and forces, they are somewhat related. They should be related. Yes. Now the question is, we have 2 charges. One is positive 2Q, one is minus Q. The question is, what will the electric field lines look like? Sure. Why should it be A? Between B and A. Well, you see, in A, everything is quite symmetric. In B, you have this heart shape close to the plus 2Q. In D, you have this heart shape in the minus Q, right, close to the minus Q. So those are the difference between A, B, and D. Okay. Mm-hmm. Okay, so there's another supporting explanation for the answer D. Any B guys? No, we don't have relativity. Any B guys? Anybody who says that the answer is B? Horizontal, why horizontal? I mean, radial, you mean? Okay. So let's see. Let's just, I mean, if you remember our previous example, how we determined the shape of the electric field lines, we just chose some sample points. We found the electric field lines at those sample points, electric field at those sample points. We know that the electric field lines should be tangent to the electric field at that point, so we just kind of sketched the line that goes tangent to all the vectors. Now we can do the same thing, a similar thing. Let's look at, well, the symmetrical points are always nice. Let's take a point right at the center. This is the center line. So this distance is equal to this distance. It is vertical. Let's look at this point. Or let's look at a point a bit lower. Now, the electric field line created by the plus 2q charge, which direction will it be? It will be upper right, right? So this is its direction. So let's call it E2q. Now, the electric field line created by the minus q, what will be its direction? Okay, right, down right. Let's call it E minus q. What can you say about the magnitudes? This one is, I mean, I already drew it like that. The distances are equal. The charge here is twice the charge over here. So the magnitude of this electric field is twice the magnitude of this electric field. Now, if you sum them up, you can just use the parallelogram law. So this will be the direction of the total electric field. It is definitely not horizontal. It is pointing a bit towards the up. So the electric field lines at the central point should be tangent to this vector. So they should be going, still they should be going up at the central point. Now if you look at this one, well, it's more clear over here, it is going down. Or, I mean, in the upper half, it is going up. In the lower half, it will be going down. The electric field line at this point will be slightly going down, if this is the horizontal. So if you look at this one, it doesn't satisfy this criteria. But if you look at this one, for example, at this point, the electric field line is pointing upward. So this is the electric field line. Now, most of you try to explain it as, okay, we have this more charge over here, so it is kind of pulling the electric field lines. Now, electric field lines are mathematical objects that we invent. You could have thought that, okay, this is, I have more charge over here, so this charge is more dominant than the other charge. So you could have said that, okay, here I have more charge, so the electric field line should look more like the electric field line of this positive 2q charge in more regions than the minus q charge. But I know that the positive q charge is, the electric field lines are radially outward, so in a larger region, the electric field line should be going out, away from the 2q. And in a smaller region, they should be going towards the minus q. Any questions on this? Any other questions? Okay, so your friend is asking this. Am I right? So let's say I have some charge Q1, and on the same line, I have some charge Q2 and the charge Q3, right? So what is the force acting on the first charge? Is it affected by the fact that this Q2 and Q3, they're on the same line? So it's like, I'm here, Sarjan is over there. What was your name? Rifat is over there. We are all along the same line. Since Sarjan is in between, I cannot see all of Rifat. So kind of the presence of Sarjan affects what I see about Rifat. So what about the electric field lines? Does the presence of this charge Q2 influence the force that this charge Q3 exerts on the charge Q1? Does it? Remember, these are point charges. Now, the answer to this one is no. It has no effect. Whether we have some other point charge Q2 over here or not, it will have no effect whatsoever on the force that the point charge Q3 exerts. So this will, F1 will still be 1 over 4 pi epsilon 0 Q1, Q2 divided by R12 squared, R12 hat, plus 1 over 4 pi epsilon 0 Q1, Q3, R13 squared, R13 hat. Absolutely no effect. Just like the case of gravity. There is a difference here though. Now there was also another question about what happens if if you remember our example of the force, we had this conductor, we placed a positive charge and a negative charge, both of them were attracted to the conductor, and was it you who was asking, what happens if the conductor has a hole? Now let's discuss a bit about the conductors. We have the electric field lines. So this is my conductor. And remember, we are always studying, we are at least at the moment, electrostatics. Statics just means that, the system might be changing in time, but at the moment that we are studying the system, all the changes have already faded away. The system is no longer changing. So we are only interested in those systems for the time being. Now we have a conductor, and let's assume that somewhere in the universe there are some charges which create some electric field lines. What are there? I don't really care. That won't be important for our discussion now. Is it possible to have an electric field line like this? Is such an electric field line possible? Why not? Why? Okay, I'm sure most of you have already memorized that the electric field line should be perpendicular to the conductors. Why? So you say that, okay, just like this, or you also claim that there's an electric field line in the conductor also. Okay. This is your friend's claim. No, there's no electric field inside. Well, I will also ask, why not? Why don't we have an electric field inside the conductor? Or why do we have the electric field on the surface of the conductor perpendicular to the surface? Why? What? The charges are accumulating where? No, if you want to put some test charge somewhere, do it. But I'm interested in this electric field line. Is such a configuration of electric field lines possible? Now, I don't care about the charges that are creating these electric field lines. I can always create some, let's say, forget the conductor. Without the conductor, I can create an electric field line that goes along a line. Now, what I do is I just put the conductor over there. How will the electric field lines be modified? Will I, at the end of this modification, have an electric field line of this shape? Even in principle, is it possible to have an electric field line of this shape? It just comes in with an angle and leaves the conductor with an angle, nothing in between. One of your friends, you had already, Fırat already said that the electric field line should be perpendicular to the conductor. Okay, that is true. So that already tells me that such a configuration of electric field lines is not possible. But my question is, why should the electric field lines be perpendicular to the conductor? Let's assume that this was possible, that this was the electric field line. And we know that the conductors have charges that are free to move. In most cases, we have the electrons that are free to move around. So let's just imagine an electron here. I have an electron. It feels this electric field. What will be the direction of the force that this electron will feel? Due to this electric field line. Okay, it has negative charge. We know that the force felt by an electric charge is nothing but the charge times the electric field at that point. Well, the electric field is tangent to the field line. Okay, so we know the direction of the electric field is tangent. Electron has negative charge, so the force it feels will be in the opposite direction. So the force that this electron feels will be in this direction. This is the force the electron will feel. No, it's at rest. Well, the electric field line is pointing in that direction. So the electric field at the position of the electron is pointing in that direction, right? Any questions up to here? Well, electron has negative charge. So if you multiply a vector with a negative number, it will be pointing in the opposite direction. So this will be the direction of the force that the electron feels. It is the direction of the force, not the electric field. The electric field is in that direction. Now, the electric field, this force has a component parallel to the surface and perpendicular to the surface. So there's a component parallel to the surface and another component perpendicular to the surface. Well, it's a conductor. So, I mean, any solid just holds all the parts that's making the solid. So the conductor will not let electron move in the direction perpendicular to the surface. It will not be able to go out of the conductor. But nevertheless, it's free to move in the conductor. There is nothing that will prevent the motion of an electron inside the conductor. But that means that if there's this horizontal component of the force, the electron feels a net horizontal component. So what prevents it from moving? Nothing. But that means that if we have such an such a configuration, it means that the electrons are moving in the conductor, but that is no longer statics. So we will induce charges in our conductor. So what will happen is if we initially have a configuration of charges somewhere in the universe such that we have such an electric field line, then I just bring a conductor there. But this conductor, due to the presence of the other charges, the electrons will move towards the right. So this part will be negatively charged. This part will be positively charged. So I have a separation of the charges now. But in this configuration, I have additional electric field. These charges create an additional electric field, and the charges will keep separating as long as the electric field has a horizontal component on the surface. So I will not have electrostatics, but when static equilibrium is established, so that is all the charges are moving, the statics will be established when the electric field do not have any horizontal component. So that is why in electrostatics, the electric field lines on the conductor have to be perpendicular to the conductor. So this whole thing will just become, let's say, away from the conductor. We will still have this electric field line. Away from the conductor, it won't have too much of an effect. But as we come closer to the conductor, the electric field line will start to bend so that it will be perpendicular to the surface. This is perpendicular, and here again it will be perpendicular to the surface at the point that it leaves. So this will be the new shape of the electric field lines when statics is established. Well, why isn't there an electric field inside the conductor? Well, here there was some electric field here, but now there's no electric field inside. Symmetry, well, I could have taken some asymmetric shape. What symmetry? There's statics. If there was an electric field inside the conductor, it means the electrons in the conductor are feeling a net force. But if the electrons are feeling a net force, they will keep moving. There is nothing that prevents the electrons from moving inside the conductor, so it won't be any statics. In statics, you cannot have an electric field inside the conductor. Let's do another example. Let's say we have, well, let's discuss this case. So how would the electric field lines look like in this case? This is a conductor, it's neutral. It doesn't have any net charge. How will it look like? Somebody else, if any volunteers. Hmm? Okay, draw a few more electric field lines, not just one. Draw a few more. So this is how it will look. Okay, this is your friend's idea. So is this correct? Yes or no? If no, what is wrong with it? Okay. So from here to there. So your friend is saying this one. We have the plus charges, minus charges, the plus Q over here. You mean we will have this one, like this? Here, okay. Okay. And that's it? So this is what you have the plus charge over here, we have the minus charges. And that's all. Well, okay. So one thing you should pay attention to, the number of electric field lines doesn't change. Meaning that if there are 3 over here, there should be 3 going to infinity. Unless they end in some negative charges. So let me remove this thing. Now this will be, your friend is kind of correct. We will definitely have such electric field lines that will be perpendicular to the surface. And from the other side, they will again start, and we will have electric field lines more or less like this. But we will also have lots of more electric field lines. So this will be more or less the shape. I mean, if you remember, if you just have a single positive Q charge, they are just pointing radially outward. Now, when you put a conductor there, it will mainly deform the electric field line that is passing through the conductor. Now, of course, we might have electric field lines also like this, another one. I mean, electric field lines can also start from these edges. Questions? No. Yeah. Because just we said in a moment that, in fact, what's actually happening here is, let's see. Now, when we put the positive charge, let's say we put the positive Q over here. There are the positive charges accumulated here, negative charges accumulating over there. And we know that the electric field at a single point is nothing but the sum of the electric fields created at that point by each one of the individual charges making our system. Now we can just imagine that, okay, forget this one for the time being. I have such a charge distribution. So what will be the electric field lines of this charge distribution? Well, let me just sketch. These are my electric field lines. These are the electric field lines created by the charge distribution in my conductor. Now to this I have to add the electric field created by the positive charge. Remember I had this plus Q over here. It will also create an electric field lines. And the electric field line that plus charge creates will be in this direction. Now, at every point, the electric field line will be just the sum of these two electric field lines. So let's see. At this point, Okay, let's look at this point. There is, of course, an electric field line passing through that point, which has more or less the shape now, like that. Oh, yeah. Anyway, it will have a shape like this. So I have an electric field line in this direction, another electric field line in that direction. So that is why the electric field line at this point is modified. Now, if I look at this point, the electric field line created by this plus charge is towards the left. The electric field line created by the charges inside my conductor is pointing towards the right. And the charges will just separate until these two electric field lines cancel each other. So inside, the electric field line created by this positive charge and the electric field lines created by this separation of the charges inside my conductor, they will exactly cancel. That is why in the final configuration, the net electric field inside my conductor is 0. Because there are two contributions there. One, as you said, there is the electric field, the contribution to the electric field from this positive and negative charges, which will be pointing towards the right. And another one, due to this positive charge, it will be pointing towards the left. And they will cancel exactly. Now, if I increase the charge over here, plus Q, what will happen is this minus charges over here will also increase. The plus charges over there will also increase. Since it's a conductor, I don't really have any control on how much charge is on each side. The only thing that will control how much they separate is the fact that inside the conductor, the electric field created by this charges in the conductor should cancel the electric field created by the outside charge. Because I know that in electrostatics, I cannot have any electric field inside the conductor. That's why there is 0 over there. Okay, if you send the charge to positive infinity, which doesn't exist, in that case, of course, you will just break away the positive and negative charges on your conductor, so you will not have any conductor. So you will not have any problem. Other questions? Yes. In electrostatics, this is not true in electrodynamics. If you have time-dependent electric fields, moving charges, this will not be true. But in electrostatics, where all the charges are at rest, this should be satisfied. And, sorry, one more thing. If you just remove some charges from here, nothing will change inside this conductor. Well, nothing will change because they are not feeling an electric field anyway. Yes. Whether the electric field is going inside the conductor or out of the conductor, they have to be perpendicular to the conductor. The shape doesn't really change. I mean, if you replace all positive charges by negative charges, the only difference is that the direction of these arrows will be different. Which one? Direction of the line. Okay. Okay. It will be changing depending on your point. I didn't understand the question. Yes. The number of field, if you have a neutral conductor, the number of field lines entering the conductor and the number of field lines leaving the conductor will be the same. Let's discuss it next week though. Next week we will be discussing what we call the Gauss theorem, which will basically be proof of this. So you are saying that we have some positive charge over here, we have some two conductors over here. You mean on this side? And what will happen? Well, I have the positive charges. Here will be negatively charged. Here will be positive, negative, positive. The electric field lines, they will enter here perpendicular. They will basically just go straight, and then they will just leave. Well, the lightning is a current where the charges are moving from one point to the other point. Here, these are electric field lines. There are no charges moving here. I don't put any charges. Other question? Nothing will change. You have the electron, some nuclei and electrons over there. If you remove it, they are not creating any force. They are not feeling any force, or they are not creating any electric field. So nothing will change, whether there's a hole in it or there's no hole in it. In particular, there will be no electric field lines inside. So if you have some charge over here, you have an object over here, and if you want to protect that object from the electric field lines, put some conductor around it. In fact, that's why if you go to the elevator, if you take the small elevator, and if you are just riding on the elevator, you cannot really talk on the phone. The strength of the signal is reduced drastically because the elevator is a conductor. It doesn't allow electric field lines to pass through. Well, the principle is the same. From the positive charges, draw electric field lines that go out. From the negative ones, draw the electric field lines that go in, and make sure that your lines are perpendicular to the conducting surfaces. Insulator. Well, we will see. I mean, in the case of the insulators, we know that the charges are fixed; they are not free to move. So the electric field on the surface of an insulator can have an angle. It doesn't have to be perpendicular, because anyway, the electrons will not be able to move inside our insulator to cancel the horizontal component of the electric field. Nevertheless, it will have some effect on the electric field. Not as drastic as this one, but it will have some. And we will discuss it, don't worry. It will be probably within a month we will be discussing it. In which one? On Tuesday? Well, at the end of the day, what we have is such a what we will have will be such a configuration. We have the positive charge Q. Okay, so this is the grounded. So here we have the negative charges. So this will be the shape, more or less. Again, everywhere is perpendicular. Now, the difference from the previous cases is that in this case, we have a net negative charge on the conductor. So we don't have any electric field lines leaving our conductor. Well, no, we won't have any electric field lines leaving the conductor. They will just come and on the conductor. No. We are in statics. They have already moved to their final destinations. And that's what happens. We only have the negative charges since it's grounded. Okay, let's give a break now, a 10-minute break. After the break, we will discuss your questions.